So we have one more application problem to consider here from section 7.2, and it's another fairly involved one. Let's get started. An obelisk 75 meters tall is located in the distance. From a balcony in an apartment building, a person determines that the angle of elevation to the top of the obelisk is 3.9 degrees and the angle of depression to the base of the obelisk is 1.4 degrees. What is the distance from the apartment building to the obelisk? So let's see here. What is an obelisk? An obelisk is like a tower, pointy tower. I think of the Washington Monument in Washington, D.C. There are obelisks in ancient Egypt made out of solid stone. So we're talking about this tall, pointy tower. So let's see here. We have let's try to draw a picture. We have the ground. And off in the distance, we have this tower that we're talking about, the obelisk. I'm just going to draw it like so. And then where we're located, we're in an apartment building. And there's this balcony. And there we are. And now it says the angle of elevation from the top of the to the top of the obelisk is 3.9 degrees. So this is from the balcony to the top of the obelisk. We kind of have this idea of this line going up like so. But now an angle of elevation must always have one side horizontal. So we need a horizontal from this balcony. That's sort of the key to understanding this problem. And then it's this angle that's 3.9 degrees. And then we're told the angle of depression to the base of the obelisk is 1.4 degrees. I guess I didn't quite draw this to scale. The 1.4 degree angle should look smaller. But again, it's an angle of depression, and it also has to have one side horizontal. And we need to add, notice how we needed to add this horizontal line from the balcony straight across to the obelisk. And then we want to find the distance from the apartment building to the obelisk, this x, this is what we're trying to describe. And then I guess we also know that the height of the obelisk is 75 meters. And so, well, I can see I have some triangles here. This horizontal line meets the obelisk at a right angle. So I actually have some right triangles in this picture, and they involve these two angles, but I don't have the measurements of any sides. Actually, this x distance is the same as this horizontal distance from the balcony straight across to the obelisk. So I want to involve x in these angles, but now I need two sides, right, to get a ratio and apply trig functions to get a ratio of sides. And so there are different ways we could proceed here, but what I really want to describe each of these two sides of these two separate right triangles. There's an upper one and a lower one. Neither one of them has a 75-meter side. What I could do is I could introduce a variable and call, say, that distance, that length, y. And I could actually introduce another variable to call this distance down here z or something, but let's see if we can avoid a third variable. And lots of problems require more than two variables in life, but here, because we know the entire obelisk is 75 meters, and we're going to call part of the height y, we can call this distance here 75 minus y, the total height minus the piece we label y. And so notice that we have introduced a second variable here. So we want to find x in this problem, but we've introduced a y to be able to describe the sides of these triangles. Now, we have two triangles, so that's hopeful. Maybe we can come up with two equations here. Let's see. We have one right triangle. I'm just going to draw the upper one, a copy of the upper one here, where this is the 3.9 degree angle. This base here is the x distance. This side is y. And then the lower right triangle, if I draw a copy of that, this is the 1.4 degree angle. This side is x. Here's the right angle. And then this is 75 minus y on that side. And for both of these triangles, I have an angle with an opposite and adjacent side. So let's go with tangent. Tangent of 3.9 degrees equals opposite over adjacent. So opposite is y over x. And in the other triangle, tangent of 1.4 degrees is equal to opposite over adjacent. Opposite is 75 minus y over x. So looks like I have two equations and two variables that I can solve. I could try to work with the tangent expressions, or I could substitute in decimals that I get from my calculator. I'm going to go ahead and substitute in the decimals that are rounded off at 4 places. For the tangent of 3.9 degrees, I get 0.0682 equals y over x. For the tangent of 1.4 degrees, I get 0.0244 equals 75 minus y over x. And so let's just maybe circle this so we can focus on what we got right now. What we want to do is we want to solve this system. Of two equations and two variables. And since I have fractions involved, I'm going to clear denominators. I'll multiply both sides by x. On the first equation, I get 0.0682 x equals y. Multiply both sides by x in the second also, right? 0.0244 x equals 75 minus y. And so it's kind of similar to the previous problem in that we have two equations and two variables, but I don't have the same situation at this point where I can just equate one side of one equation with one side of the other, right? I don't have the same variable isolated in both. But I do have y isolated in this first equation, so I could make a substitution into the second equation. I can replace y in the second equation with the left-hand side of this first equation. So I'm going to recopy here. 0.0244x equals 75 minus, instead of y, let me write down 0.0682x, right? I'm substituting that in for y. So I'm using the information from the equation on the left in the equation on the right, and this gives me an equation in just x, and actually we're not too far from solving right now. So I'm going to go to another sheet of paper here. I have 0.0244x equals 75 minus 0.0682x. And there's really not much more left to do here. I just got to add 0.0682x to both sides. And let's see, what do I get? I have 0.0926x equals 75. So x is going to be 75 divided by 0.0926. And when I check that on my calculator, it comes very, very close to 810 meters. And that's actually what we want. We were interested in finding a value for x, the distance from the apartment building to the obelisk. So let's just label that distance from the apartment building to the obelisk. We don't need y here because really x is all we were after. We introduced y to help us set up the system, but just for the record, if you went ahead and you might have used a technique where you found a value for y first, y is about 55.24 meters if you go back and solve for y. But you don't have to. You could just solve it. Really it was only x that we were after. We got x equals 810 meters, and we've solved this problem. So I guess I want to try to keep the answer appearing along with some of the original information from this obelisk problem. And we're through with, I think we're totally through with 7.2.